Hey Phys 1 kids, Campbell here. In this video, we're going to talk about the oscillation of pendulums. Now, what is a pendulum? Well, a pendulum simply is a mass at the end of a string. And that string, or in this case cord, it doesn't stretch. That's important because then it's kind of like a spring on a string. And it also, we're going to say that that string has negligible mass. Why does a pendulum oscillate? Well, clearly right here, we're at the equilibrium position, right? The equilibrium position for something that oscillates is always where it would be at rest if there's no restoring force acting on it. But if I pull my mass out to the side and I let go, right, it starts to swing, and it swings in simple harmonic motion. So why does it swing? Well, because as soon as I pull it out to the side here, the force of gravity now, which points straight down, is now has a component here which is trying to return it back to its equilibrium position, right? This would be my equilibrium position down here. And so if I pull it off to the side, the force of gravity wants to restore it back to the equilibrium position. So the force of gravity acts as a restoring force. So my pendulum will swing back and forth. Now, when it gets here to the equilibrium position, right now the force of gravity is straight down, so it's not acting as a restoring force there, which is why the pendulum would be at rest in that equilibrium position. But it has speed when it gets down here, which means it's going to keep swinging in that direction because it has some velocity. And once I do that, right, the force of gravity wants to pull me back towards that equilibrium position. So the force of gravity acts as a restoring force. Now, a lot of times in pendulums, you're going to be asked to find the swing speed. Well, there are two ways to go about this. One, if you have information about forces, then don't use conservation of energy. You want to use the stuff we learned about in the circular motion unit. So the sum of the forces are mv squared over r, because a pendulum is really just making a circle, right? It's just a part of a circle. Now, if you don't have information about forces, but maybe you have information about height, or maybe you have information about the speed at the lowest point and you want height, then you want to use the law of conservation of energy. Now, just like springs, we went through this process of figuring out where things are max and where things are min. So we're going to do that same exact thing for my pendulum. And we're going to start down at the energy part. So let's talk about the energy of the swing. When I pull it off to the side, right, I'm at a maximum height, which we would call the amplitude, like for a spring, and I let it go. And notice that every time it reaches that amplitude again, it stops, and then it starts to swing back. So that means when I am at what we'll call our amplitude, or maximum height, which would be here or over here, right, I swing back and forth, I'm going to have a maximum gravitational potential energy. So my gravitational potential energy is a max at the amplitude or the maximum height. Now remember, that was the same thing for a spring. Anytime we were at amplitude, we had a maximum of spring potential energy. When I swing down here, right, down here I'm at the lowest point, so we would maybe call that a height of 0. And so in that case, my UG, my gravitational potential energy, is 0 at the equilibrium position. So here, UG is 0. So what does that mean then about the kinetic energy of the swing? So when I'm swinging, right, I stop when I reach maximum height. So at the amplitude, my kinetic energy is equal to 0. So at max height, or the amplitude, height, k equals 0, which means that when I get to the point where gravitational potential energy is 0, then at that point, that lowest point, I have k max. So k is a maximum at the equilibrium position, which is the lowest point in the swing. Now, that means we can go back to looking at speed. So at the amplitudes, right, if I have 0 kinetic energy because I've stopped, that means that's also true that my speed is 0, right? In order to turn around and come back, I have to stop. So the speed is 0 at my amplitudes or my maximum height, And if kinetic energy is a maximum at the lowest point of the swing, then my speed must also be a maximum at that lowest point. So V is a max when I'm at equilibrium. So V max at equilibrium. So the lowest point in the swing. Anywhere else, right, I'm somewhere in between my amounts of gravitational and potential energy. So I have my speed here is somewhere in between. So when I reach here, right, my velocity is somewhere in between V max and 0. So somewhere in between that range is my speed. What about acceleration? Where would the acceleration of this be the greatest? Well, think about springs, because we have the same sort of oscillation, right? For springs, our speed was a max when we were at the equilibrium position. Our force and acceleration were a max at amplitudes. Well, that's true here too. Because the angle that the force vector makes with that displacement, that motion, is bigger out here, I have a bigger force out here. So if I have a bigger force at amplitudes, that means my acceleration, right, mass, acceleration is force over mass, is also a maximum. So acceleration, restoring force go hand in hand. They're a maximum at the amplitudes. And remember that the amplitudes are where I have my maximum height. So here, F and A are max. Now, when I get back to the middle here, remember that force of gravity was pointing straight down, which means it's not a restoring force anymore. So that means when I'm at the equilibrium position, I have 0 force and 0 acceleration. So at the equilibrium position, both F and A equals 0. So when I'm here, F and A equals 0. Now that doesn't mean I stop, right? We know we're not stopping. Just because I don't have acceleration doesn't mean that I don't have any motion, that I don't have any speed, right? It just means I'm not changing the rate of my speed anymore. But so I reach a maximum speed with 0 acceleration and 0 force at the equilibrium position, and as I move away from that equilibrium position, I slow down till I get to maximum height, and then I speed up. Now, once again, because the angle with the force vector is making to the direction of motion, since this is changing, that means my force and acceleration magnitudes are changing, which means I cannot use kinematics to solve for spring speed. So once again, no kinematics, just like with springs. So let's do a little bit of math on a problem and see how we would solve this. So I want to know what the speed is when this pendulum passes through its lowest point. I know that the length of the pendulum, this L value, is 0.76 meters, and that the mass is 0.365, so that's 0.365, sorry, kilograms, don't work in grams. It's released at an angle of 12 degrees to the vertical. And what I want to know is what's the speed? Well, I don't have information about forces here, so this is a good example of when I want to use energy. So I know that up here, right, energy is all gravitational potential energy, and down here my energy is all kinetic energy. So that means I have gravitational potential energy at the top of the swing and kinetic energy at the bottom, and it's all kinetic energy because we're going to call that the lowest point of the swing. So we have mgh is equal to 1/2 mv squared. So if I rearrange this, I get the square root of 2gh. Notice that my masses cancel, so I guess I didn't even have to care about that. Now, I need h, right? But this is h, and they didn't give me h. They gave me a value for L, the length of the string, and they gave me an angle of 12 degrees. Well, this is L also, right? This is my 0.72 meters, and this is my h value. So if I make a triangle here, and I find out what this little piece of the triangle, I'm going to call that y. If I find out what this little piece of the triangle is, and I subtract it from my total L, I could get h, right? H here is the difference between the total length of the string, L, my 0.76 meters, and this little segment, which is the cosine side of my triangle. So we'll call that y, but what y is, right, is the cosine of theta would be y over L, right? The hypotenuse of this triangle, this is a right triangle, is L. So that means that my height is L minus L cosine theta. All right, so that means we can go ahead and start solving this. 2 times g, which is 9.8, times this quantity, L, which is 0.76, minus 0.76 cosine of theta. Do that, get a square root. If you do that correctly, you should get a speed of 0.58 meters per second. All right, so energy in this case, because we have information about speed. I mean height, sort of. Oop, there we go. Sorry about that. All right, now if we think about the restoring force, right, here's my force of gravity, and this triangle here with my angle to the vertical of how far I pull out the mass happens to be the same as this triangle here. And so we could play around with angles, right, which means that that's that angle here. And so this force of gravity, we'll call it force of gravity in the x. This is what that is. That's not some new force. That's my restoring force. All right, that force of gravity in the x would be equal to mg sine theta. Now, we call it a negative because it's a restoring force, so it's bringing me back to, so whenever my position is positive, the force is pulling me back, and so it's a negative force. Now, if we think about this triangle here, this angle theta is the sine of that angle is x over L. So for small angles, and small angles would be less than 12 degrees, the sine value is very, very small. So this we could just plug in for sine theta. And so we get an equation that looks like this. And not that this is important for you to be able to derive, but if you think about this equation, it kind of looks like the spring force equation, right? The spring force equation is negative kx. So we can kind of think of this equation like the spring force equation. Now, again, I don't know that you will need this equation, but it brings us to finding the period of a pendulum. So here's the period of a spring, right? In class, we talked about the period of a spring, 2 pi times the square root of the mass on the spring divided by the spring constant. So if we plug this in for k, we end up with this. So this is the important part. I want you to write this down. The period of a spring is 2 pi times the square root of L, the length of the string, over g, the acceleration due to gravity. Now, I want you to pay attention to that equation because it is very different from the spring equation. Notice that there is no mass in this equation. The mass ends up canceling. So for the period of a pendulum, mass doesn't matter. Matter no mass. Mass don't matter. The length of the string matters, right? The longer the string is, the longer the period is. And acceleration due to gravity, right? That's really the acceleration of that pendulum back and forth. And so the higher the acceleration due to gravity is, like if we went to Jupiter, it would swing a lot faster, right? A lower period than if maybe we went to the moon where the acceleration due to gravity is small. And then the period, that force would be less. So the period would be longer. So what we're going to do in class actually is you're going to do a little lab to prove that that is true. Yay, lab! Last question for you. I want to know, what is the length of a simple pendulum which has a period of 2 seconds? See if you can solve this. And I'll see you in class, and we'll see if you did it right. So I'll see you in class.